Every night, astronomers peer into the vast expanse of the cosmos, their telescopes trained on distant stars in a relentless quest for habitable worlds and faint whispers of alien radio signals. So far, the universe has remained stubbornly silent. No definitive signs of life have emerged from the dark void. But does this mean their efforts are futile? Are we truly alone in this immense tapestry of space? This question carries profound weight, as its answer shapes our understanding of humanity's place in the grand scheme of the universe. One compelling idea, known as the rare Earth hypothesis, suggests that perhaps we shouldn't expect to find life scattered across the stars. According to this theory, Earth might be an extraordinary anomaly, a singular cradle of life in an otherwise barren cosmos. But is this hypothesis sound? To explore this, let's start with the big picture. Zoom in on the hypothesis itself, and then examine recent discoveries to see if they align with or challenge this perspective. Here's the roadmap we'll follow. We'll dive into a topic that's fresh for discussion, weaving together a variety of concepts that promise to captivate your curiosity. You've likely encountered the notion of a star's habitable zone, that sweet spot around a star where conditions are just right for liquid water to exist, neither too scorching nor too frigid, often dubbed the Goldilocks zone. It's the region where exoplanets might have the potential to support life as we know it. But did you know that galaxies themselves have habitable zones? Not every galaxy is equally hospitable to life. Stars farther from a galaxy's core tend to have lower metallicity, a term astronomers use to describe the abundance of elements heavier than helium. These heavier elements, essential building blocks for planets and life, are forged in the fiery hearts of massive stars and scattered into space by supernova explosions. Such stellar furnaces are far more common near the bustling galactic center, where raw materials are plentiful. Consequently, stars on a galaxy's outskirts often lack the critical ingredients needed to form rocky planets capable of sustaining life. Closer to the galactic core, however, a different peril emerges. Most spiral galaxies, like our Milky Way, harbor supermassive black holes at their centers. These cosmic titans can unleash torrents of X-rays and gamma rays, bathing nearby regions in lethal radiation. Any exoplanet orbiting too close would be relentlessly bombarded, rendering it uninhabitable. Life, as we understand it, could never take root under such harsh conditions. Then there are the galaxy's spiral arms, stunning features of dense star formation that sweep outward from the core. While beautiful, these regions are treacherous for life. Stars within the arms frequently pass near one another, their gravitational interactions disrupting the delicate orbits of orbiting planets. Imagine Earth suddenly veering onto Mercury's sun-scorched path. Any budding life would be snuffed out in an instant. Additionally, the spiral arms are hotspots for supernovae, which erupt with deadly radiation that sterilizes anything in their vicinity. So, the Gulick habitable zone strikes a delicate balance. It's a region close enough to the core to benefit from sufficient metallicity, yet distant enough from the center and spiral arms to avoid catastrophic gravitational tugs and radiation overloads. Our understanding of this zone is still evolving, and we're only beginning to map out which parts of the Milky Way, or any galaxy, might be suitable for life. In the Milky Way, these constraints likely render the vast majority of stars unfit to host life-bearing planets. Even among the remaining candidates, a star must be of the right type and possess a planetary system structured in a way that nurtures life. Once, we assumed every star had a habitable zone where liquid water could theoretically exist. But this view oversimplifies the complexities of stellar and planetary dynamics. Take low-mass stars, for instance. These dim, cool stars emit far less visible and infrared light than their brighter counterparts on the main sequence, like our Sun. Yet they can unleash intense bursts of X-rays and gamma rays. While their habitable zones might technically allow for liquid water, the radiation levels could shred complex molecules, obliterating any chance of life taking hold. Our Sun, by contrast, is remarkably stable, with its luminosity fluctuating by less than 0.1%. Other stars, however, can vary wildly, some by as much as 500%. Such drastic swings shift the boundaries of their habitable zones, plunging planets in and out of life-friendly conditions. A world might bask in habitability one moment, only to freeze or boil the next, erasing any prospects for sustained life. Even if we pinpoint a star with the right characteristics, the presence of a life-friendly planet is far from guaranteed. The arrangement of a planetary system plays a pivotal role. In our solar system, rocky planets like Earth huddle close to the Sun, while gas giants like Jupiter orbit farther out, a configuration that's surprisingly rare. Most exoplanetary systems discovered so far feature either all rocky worlds or gas giants parked perilously close to their stars, dubbed hot Jupiters. Our system's unique layout, with its blend of inner rocky planets and outer giants, may have been a key factor in life's emergence here. The number and arrangement of planets in a system also matter. Systems with just one or two exoplanets often exhibit highly elliptical orbits, causing planets to swing in and out of the habitable zone over the course of their year, yet another strike against life. In contrast, systems with multiple larger planets can develop orbital resonances, where gravitational interactions stabilize orbits into near-circular paths. This stability allows a planet to linger in the habitable zone consistently, boosting its odds of supporting life. Orbital resonance is a complex dance of gravitational harmony. It keeps planets in their proper places, preventing chaotic deviations. If Earth began drifting too close to the Sun, these resonances would tug it back into line, and vice versa. This equilibrium has been vital to our planet's long-term habitability, but even with stable orbits, the right mix of rocky and gaseous planets, and a star of the ideal type, the chances of finding life remain slim. Consider Jupiter's role in Earth's story. Models of the early solar system suggest this gas giant was instrumental in life's development. Its gravitational influence shepherds the asteroid belt, locking countless rocky fragments between itself and Mars. Without Jupiter, Earth would face a relentless barrage of impacts, making it nearly impossible for life to gain a foothold, or even begin. In the solar system's infancy, Jupiter briefly spiraled inward, threatening to obliterate the inner planets. Fortunately, its resonance with Saturn intervened. Saturn's gravitational pull yanked Jupiter back, averting disaster and preserving Earth and Mars. This intricate interplay underscores the notion that a specific planetary configuration, complete with a Jupiter-like guardian, may be a prerequisite for life as we know it. Yet even this isn't the full picture. A planet's size, composition, and geological activity are equally critical. Too small, and a planet struggles to retain an atmosphere or liquid water. Mars is a stark example. Its thin air and dry surface, a testament to its diminutive stature. Too large and excessive gravity could trap a crushing atmosphere, stifling life. Atmospheric composition also matters. Venus, despite orbiting within the Sun's habitable zone, suffocates under a thick blanket of carbon dioxide, its surface hotter than a furnace. Plate tectonics, Earth's restless shifting of continental plates, further complicates the equation. This geological process, driven by the churning of molten rock in the planet's core, shapes mountains, triggers volcanic eruptions, and carves oceanic trenches. Many scientists believe life first sparked near hydrothermal vents, fissures on the seafloor fueled by tectonic activity. Without tectonics, those primordial cradles might never have formed. Tectonics also sustains complex life. The movement of plates recycles nutrients and regulates the carbon cycle, stabilizing Earth's climate over eons. This dynamism stems from the planet's molten, iron-rich core, which generates a magnetic field. That field shields Earth from the solar wind, a stream of charged particles that would otherwise strip away the atmosphere. Mars, lacking a robust magnetic field, lost much of its air to this cosmic erosion. Earth's tectonic vigor owes a debt to an unlikely ally, the Moon. Our lunar companion is unusually large, weighing in at 27% of Earth's mass, a rarity among planetary moons. Its gravitational pull stirs Earth's oceans, creating tides that heat the planet's mantle through friction. Without this lunar influence, tectonic activity might stall, undermining life's prospects. The Moon also steadies Earth's axial tilt, the gentle 23-degree lean that gives us seasons. Without this stabilization, wild wobbles could plunge the planet into climatic chaos. Imagine then an exoplanet ticking all these boxes, positioned in a galaxy's habitable zone, orbiting a stable star nestled in a balanced planetary system, with the right size, composition, tectonics, and a massive moon. Would life thrive there? Quite possibly. Scientists are probing Mars for clues, seeking traces of ancient life from a time when it boasted oceans, tectonics, and a thicker atmosphere. If evidence emerges, it could bolster the case for life on distant worlds, albeit simple life, akin to bacteria. Complex life, like multicellular organisms or intelligent beings, demands even rarer conditions. Earth hosted life for at least 3.5 billion years before anything sophisticated appeared. For most of that time, only single-celled organisms prevailed. Then, around 540 million years ago, the Cambrian explosion ignited a surge of diversity. Following a glacial epoch, melting ice flooded the oceans with nutrients, sparking an algal bloom that oxygenated the atmosphere. Tectonics sculpted the mountains that supplied those nutrients, making this leap possible. Within millions of years, life evolved from simple, sponge-like forms to crustaceans, squid, vertebrates, and starfish. Yet even these Cambrian marvels were far from intelligent. The journey from single cells to complex ecosystems hinged on flukes, random cellular collaborations that took eons to coalesce. Multicellularity itself may be a cosmic stroke of luck, its odds of replication vanishingly small. To summarize, a planet needs a staggering confluence of factors to harbor life: a galactic sweet spot, a suitable star, stable orbits, the right planetary neighbors, optimal size and composition, active tectonics, a hefty moon, and a natural upheaval to spark complexity. Earth's uniqueness seems almost miraculous, suggesting duplicates are exceedingly rare. But recent findings complicate this narrative. Moons like Europa, Jupiter, and Enceladus, Saturn, harbor subsurface oceans and possible hydrothermal vents, potential havens for life. If even simple organisms lurk there, the rare Earth hypothesis falters, replaced by a broader vision of habitability that includes icy satellites. With gas giants common in the galaxy, and many likely hosting similar moons, the tally of life-friendly worlds could soar. So, are we alone? The search continues, each discovery peeling back the universe's secrets. Earth may be rare, but life's tenacity might yet surprise us. The search for a twin to Earth might never bear fruit. Yet, it seems increasingly plausible that somewhere out in the vast expanse of space we could stumble upon worlds, and perhaps even forms of life, far stranger and more fantastical than anything we've encountered on our own planet. So, what do you think? Are we truly alone in the universe? Astronomers have already cataloged thousands of confirmed exoplanets within our Milky Way galaxy alone. By their estimates, though, the total number of such worlds in our galactic neighborhood could exceed 50 billion, and that's just one galaxy. If we extend our imagination to include the countless other galaxies scattered across the cosmos, the numbers become almost unfathomable. With such staggering odds, it's hard to swallow the idea that intelligent life emerged only on this one tiny speck of a planet we call home. But then a perfectly reasonable counter-argument arises. If intelligent life is so common, why haven't we heard from any extraterrestrial civilizations? Not long ago, I had the chance to visit a modest little aquarium. It wasn't a grand facility by any means, just a handful of tanks, but it captivated me nonetheless. I found myself lingering by each exhibit, peering into the watery worlds housed within. I watched the fish glide through the water with an effortless grace, some resting in the shade of artificial tropical plants. A few darted away as if shy of my gaze, while others seemed engrossed in their own affairs. And then there were those who stared back at me, their curiosity as palpable as my own. What struck me most was their lack of fear. They seemed at ease, secure in their sheltered environment. It felt in a way like they were at home. But as I stood there, I couldn't shake a nagging thought. Aquariums, like oceanariums, are artificial constructs. For the aquatic creatures of our world, these places offer safety and a semblance of freedom. Yet, from another perspective, they represent a human intrusion into the natural order. We've plucked these animals from their wild habitats, deeming them beautiful or rare, and in doing so, we've arguably diminished their quality of life. They're confined, their existence shaped by our whims. This duality makes aquariums, and by extension zoos, deeply ambiguous spaces. They're showcases of nature's wonders, yet also reminders of our tendency to control and contain. I wonder where the astronomer John Ball got the spark for his idea back in the 1970s. Was he standing by an aquarium tank, lost in thought, or did it strike him elsewhere? Regardless, he proposed a striking notion. What if humanity itself is living in a zoo, blissfully unaware of our captivity? The concept caught on, gaining traction first among scientists and later seeping into the realm of science fiction. Initially dubbed the zoo hypothesis, this idea posits that we're part of a cosmic enclosure. However, since it lacks testable evidence, some prefer to call it the zoo scenario. It's a speculative answer to a question famously posed by the Italian physicist Enrico Fermi in 1950. Where is everybody? Fermi's paradox highlights a glaring contradiction in our understanding of the universe. If extraterrestrial life, especially intelligent life, is not just possible but probable, why haven't we seen any sign of it? Is there a biological or sociological reason for this silence? The zoo scenario offers one explanation, and by now you've likely pieced it together. In essence, the zoo scenario suggests that the reason we haven't detected alien life is that Earth is a designated preserve, a galactic wildlife sanctuary of sorts. Advanced civilizations may indeed exist, perhaps in droves, but they've chosen to leave us undisturbed. Picture humanity tucked away in one of the Milky Way's spiral arms, isolated from the bustling hubs of cosmic society. It's not unlike how we set aside pristine tracts of land on Earth for animals to thrive. untouched by our sprawling cities and highways. The zoo scenario draws heavily on humanity's own history. We've dissected nature, harnessing it for our bridges, skyscrapers, farmland, and sun-drenched vacation resorts. Yet we've also carved out pockets, national parks, reserves, zoos, and oceanariums, where wildlife can persist under our watchful eyes. If we use these spaces to study and admire Earth's creatures, isn't it conceivable that supremely advanced civilizations might do the same on a grander scale? In this view, Earth isn't just a planet, it's a living exhibit. But unlike our zoos where we observe lions or elephants, these extraterrestrial overseers are studying us. The prime directive variation of the zoo scenario takes it a step further. It suggests that intelligent civilizations have collectively agreed to leave habitable planets alone, having reached a state of equilibrium, sometimes called a steady state. In this phase, they no longer feel the urge to expand aggressively or colonize new worlds. Science fiction paints vivid pictures of such a future. Civilizations dwelling in massive, self-sustaining arcs, no longer tethered to planetary systems or even orbiting conventional stars. Perhaps they harness the rare but colossal energy of hypergiant stars to power their societies. In this era, information becomes the ultimate currency. Earth, then, might be more valuable to them as a pristine data source than as a territory to conquer. When we visit zoos, we marvel at how a tiger paces its enclosure or a monkey swings between branches. Similarly, these advanced beings might observe Earth over eons, tracking the journey of life from fragile single-celled organisms to rocket-building engineers. So how could we coax these cosmic zookeepers into revealing themselves? Imagine strolling through a zoo when a zebra suddenly locks eyes with you, stomps its hoof, and taps out a sequence of prime numbers. That would shatter the boundary between observer and observed, forcing us to respond. As Mehdi Douglas Vakucha, a thinker on this subject, once put it, we could do the same, beam powerful, deliberate, information-rich radio signals toward nearby stars. It's a bold move, a cosmic knock on the door. Among the zoo scenario's many offshoots, one testable idea stands out: the planetarium hypothesis. This theory probes just how far an alien civilization might go to keep us in the dark. A planetarium, after all, is a theater of illusions. It projects dazzling images of stars, constellations, and planets onto a dome, creating the sensation that those distant realms are within reach. But it's a facade, a carefully crafted simulation. The planetarium hypothesis suggests that our entire universe might be a projection, designed to convince us that space is devoid of intelligent life. Consider the Voyager probes. Voyager 1 and 2 have ventured roughly 150 and 124 astronomical units from Earth, respectively. At such distances, any simulation would start to show cracks, imperfections in the fabric of our perceived reality. Testing this could yield clues that things aren't as they seem. Some latch onto the planetarium idea with fervor, claiming space itself is a hoax, a dome, or a projection. But this theory raises more questions than it answers. For one, it ascribes human-like motives to aliens. If a civilization pursues technological advancement, it likely values curiosity and scientific inquiry, traits that could drive them to study Earth. Yet why would every alien society agree to this non-interference pact? If the galaxy teems with diverse cultures, wouldn't at least one rogue faction break ranks for its own gain? Perhaps there are only a handful of civilizations, or even just one. Still, the scenario assumes universal compliance, with all aliens shielding us from contact or invasion. Why would they bother? What makes humanity so special? Maybe we're overestimating our significance. Perhaps these beings aren't our intellectual kin, but entities so advanced that they can observe and analyze us without ever needing to say hello. Picture a single, omnipotent civilization imposing this rule on all others. If power is concentrated in one species' hands, dissent becomes irrelevant. Lesser societies would have no choice but to fall in line. This, however, implies a level of interstellar coordination that's hard to fathom. Mathematical models of galaxy-spanning communication highlight the challenge. Light speed limitations mean civilizations would need to emerge near simultaneously, persist for millions of years, and cluster within the galaxy's habitable zone to maintain reliable contact. These logistical hurdles leave scientists divided on whether a dominant civilization could enforce such a universal code. The zoo scenario, then, hinges on a delicate balance of conditions, a sobering thought. It suggests that even if alien life exists, we might never know it because they've chosen to stay hidden. But if the zoo hypothesis feels far-fetched, consider an even wilder alternative: the galactic quarantine. Here, aliens recognize that contact would shatter our cultural foundations. Instead, they bide their time, subtly preparing us for an eventual meeting, patiently, methodically, without haste. I adore animals and cherish their presence, yet I'm acutely aware that keeping them denies them agency. If the zoo scenario holds truth, it's an unsettling injustice. A network of civilizations deciding our reality for us, concealing the universe's true nature, that feels fundamentally wrong. I'd argue the cosmos doesn't operate that way. Perhaps we're simply waiting for an old adage to prove itself. All that is hidden will be revealed. Since humans first emerged, we've climbed from cave dwellers to moonwalkers, reshaping our world to suit our needs. More crucially, we've pursued knowledge relentlessly. But is there an endgame? Will we ever reach a point where there's nothing left to discover? To survive the challenges ahead, humanity must ascend to new heights of development. In 1964, Soviet astrophysicist Nikolai Kardashev devised a scale to measure a civilization's technological prowess based on energy mastery. You might know it as the Kardashev scale. It outlines 3 tiers. Type 1 harnesses all energy on its planet, a planetary civilization. Type 2 taps its star's full output, a stellar civilization. Type 3 commands an entire galaxy's resources, a galactic civilization. Kardashev stopped at Type 3, deeming it the pinnacle. Later thinkers, like sci-fi author Helga Kautz, pushed further, envisioning a Type 4 that exploits a galactic supercluster's energy. Today, we're not even a Type 1, more like a Type 0.7, inching toward planetary mastery. The scale underscores our potential and our limits. Could we one day join the ranks of those watching us from afar? Or are we destined to remain exhibits, peering out from our cosmic enclosure, wondering who or what lies beyond? Imagine a civilization so advanced that it harnesses the energy of the entire universe. This is what we might call a Type 5 civilization on the Kardashev scale, an entity capable of tapping into the boundless power that fuels stars, galaxies, and the very fabric of cosmic existence. Within this grand framework, there exists a subtype, a Type VB civilization, which possesses the remarkable ability to tweak certain fundamental aspects of universal physics. It's a mind-boggling concept, altering the rules that govern reality itself. And then, pushing the boundaries even further, we arrive at a Type 6 civilization. This pinnacle of development can not only wield the energy of its own universe, but also reach beyond, drawing power from other universes within a sprawling multiverse. These extraordinary entities are often referred to as non-Kardashev civilizations, transcending the traditional scale devised by Nikolai Kardashev to measure technological progress based on energy consumption. It's evident that humanity is nowhere near achieving Type 6 status. We're still taking our first tentative steps on this cosmic journey, barely scratching the surface of what's possible. Yet, it's not entirely fair to dismiss the idea as unattainable. If we continue to evolve generation after generation, pushing the limits of science, technology, and imagination, who's to say we can't someday reach such heights? Every monumental achievement begins with a spark of thought, a vision of what could be. To predict the future, we must first dare to create it. So, let's embark on that creative exercise and explore what a Type 6 civilization might look like. Picture a time when humanity has ascended to godlike status. At the level of a Type 6 civilization, people would wield absolute dominion over their universe, shaping it according to their desires. By then, we'd have unraveled one of the greatest mysteries. Are we alone in a single universe, or are we part of an infinite multiverse? If the latter proves true, we'd traverse this vast network of realities with ease. The key to such interstellar and interdimensional travel? Wormholes, tunnels through the fabric of space-time that collapse vast distances into mere steps. Today, wormholes remain a tantalizing theoretical concept, born from the equations of general relativity. But for a Type 6 civilization, they'd be as commonplace as bridges are to us now. Imagine a journey that would take thousands of years in conventional spaceflight reduced to a matter of minutes. The energy required to sustain such feats would be incomprehensible to our current understanding, drawn perhaps from sources we can scarcely fathom, like the elusive dark matter that permeates the cosmos. This mysterious substance, invisible yet gravitationally potent, could become the ultimate fuel for a civilization that has mastered every nook and cranny of scientific knowledge. At this stage, science wouldn't just be a tool, it would be an art form, perfected to its utmost potential. Every field, from quantum mechanics to biology, would reach its zenith, granting us an unparalleled understanding of existence. This mastery would redefine what it means to be human. Disease and death, relics of a primitive past. Nanotechnology would repair our bodies at the cellular level, reversing aging, regenerating organs, and healing any injury imaginable. We'd transcend the need for medicine as we know it, our physical forms becoming infinitely adaptable. Transportation, too, would become obsolete. Why bother with vehicles when teleportation is an option? The laws of physics, once rigid and unyielding, would bend to our will, serving as the building blocks of a blissful, effortless existence. Research fields like theoretical physics might even fade away, not because they failed, but because there'd be nothing left to discover. We'd have mapped the entirety of natural law, turning it into a playground for our ambitions. Our curiosity wouldn't stop at physics. A Type 6 civilization would catalog every life form in the universe, from the simplest microbes to the most complex sentient beings. Better yet, we'd learn to create life from scratch, tailoring it to our specifications. Natural disasters, earthquakes, hurricanes, volcanic eruptions would no longer pose a threat. We'd control the elements, adjusting climates to suit our preferences or neutralizing storms before they form. An asteroid hurtling toward Earth? A minor inconvenience. We'd redirect its path or dismantle it entirely with a flick of our technological wrist. But perhaps the most profound leap would be our transcendence beyond the physical. A Type 6. Civilization might abandon corporeal existence altogether, uploading consciousness into a non-physical dimension of our own design. Freed from the frailties of flesh, aging, sickness, mortality, we'd exist as pure intellect, an eternal collective unbound by time or space. In this cloud of consciousness, resources would be limitless. Energy, matter, and information would flow endlessly, far exceeding anything we could ever consume. Each individual could claim their own planet if they wished, sculpting it into a personal paradise. The sheer abundance would defy description, every need met, every dream realized. It's hard to fully capture the scope of what such a civilization could achieve. What else might we envision? Perhaps the ability to rewrite history, simulate alternate realities, or commune with beings from other dimensions. The possibilities stretch beyond the horizon of our current imagination. Doesn't it sound like a delectable future? Before we get too carried away, though, let's ground ourselves. There's another type of civilization I nearly overlooked. Type 0. That's us, humanity as it stands today, fumbling along at the base of the Kardashev scale. Experts estimate it'll take at least a century to claw our way up to Type 1, where we'd harness the full energy output of our planet. It's a daunting endeavor, riddled with obstacles that could halt our progress, or worse, erase it entirely. One chilling explanation for our slow ascent is the Great Filter, a hypothesis tied to the Fermi paradox. Economist Robin Hanson proposed this idea to address why we haven't encountered other advanced civilizations. The Great Filter suggests there's a barrier, some insurmountable challenge, that prevents most species from reaching a detectable level of advancement. In the context of the Kardashev scale, it's the hurdle keeping us from climbing higher. What might this filter be for humanity? Resource depletion is a prime candidate, a Type 1. Civilization requires an energy output of roughly 10^16 watts, a staggering leap from our current capabilities. To get there, we'd need to boost energy production by a factor of 100,000. Much of that initial push would rely on fossil fuels, which are finite and already straining under environmental pressures. Estimates vary, but we might have only 50 to 100 years before these reserves run dry. If we exhaust them without a viable alternative, we risk sliding backward, unable to sustain even our present industries. An ambitious solution is the Dyson sphere, a hypothetical megastructure encircling a star to capture its energy output, about 400 septillion watts per second from the sun alone. It's a dazzling concept, but building it poses its own problems. The raw materials, metals and minerals, might not exist in sufficient quantities within our solar system. And that's just one hurdle. Our technological progress has birthed side effects that threaten our survival. Climate change looms large, its impacts intensifying with each passing decade. Extreme weather, droughts, floods, wildfires, ravages the globe, while polar ice melts and temperatures climb. If unchecked, these shifts could render Earth inhospitable long before we reach Type 1. Then there's the specter of nuclear annihilation. As of 2020, over 14,000 nuclear warheads dot the planet, each a potential trigger for global catastrophe. A single misstep could reduce civilization to ash. Another unsettling possibility lurks in the shadows, a hostile alien intelligence. Some theorize that advanced civilizations lie in wait, watching for species like ours to develop detectable technologies, only to swoop in and erase them. If true, the Great Filter might be an external force, activated the moment we grow too loud. Survival could mean staying silent, halting our progress to avoid notice. But that choice traps us at Type 0, forever stunted. Reaching Type 6 feels like a distant dream when even Type 1 seems so elusive. Yet the latter is within reach if we commit to a steep, steady climb. The next century holds unprecedented promise for scientific breakthroughs, if we can unite our efforts. Pooling global resources, expertise, and willpower could propel us forward, but that's easier said than done. Human history is a tapestry of conflict, wars, trade disputes, territorial squabbles. Today, we grapple with humanitarian crises, political strife, and inequality. Many argue that space exploration or futuristic tech is a luxury we can't afford when immediate problems demand attention. Without collective resolve, Type 1 slips further from our grasp, let alone Type 6. Our actions now ripple into the future, shaping whether humanity thrives or falters. By 2120, we might be debating the leap to Type 2, or clawing our way out of a new dark age. The choice is ours. The clock is ticking. Will we rise to meet the challenge, or let the great filter claim us? The stakes couldn't be higher.